There we go. So welcome everybody to what is the fifth seminar of the School for Public Health Research Natural Experiment Network. Today I'm very happy that we have a speaker from the University of Exeter who won't be talking about natural experiments as such, but who's been working on a very interesting method of triangulation of data, and I think that's something very important for natural experiments as well. And that's why I invited him to give a talk to us and see what it's all about, and see if we can do something interesting and something good with this for the improvement of future natural experiments. So it's my pleasure to introduce Professor Jack Bowden from the University of Exeter. Jack, the virtual floor is yours.
Thanks very much, Frank, for inviting me. I'm going to be talking today about some recent work I've been doing on sort of trying to design a quantitative framework for triangulating causal inference methods, and I've got a couple of applications of this approach, which is still sort of a work in progress, but a sort of an example in cardiovascular medicine, and then an example in type 2 diabetes. That work is led by one of my PhD students in Exeter. Okay, so this talk is all about trying to understand what treatments work, and of course, you know, we always talk about the gold standard form of evidence being from a randomized trial. So if we could randomize people into two groups, one group they receive the treatment and one group they receive the control, and we looked at outcomes across those two groups at the end of the trial, then because those groups should be approximately balanced with respect to all measured and unmeasured characteristics, then we can attribute any differences between those two groups to the treatment itself with a very high degree of certainty. And it also gives us an answer to quite a precise question as well. You know, what would be the effect of, assuming these people are exchangeable because of randomization, you know, what would be the effect of giving everybody this treatment in the trial versus what would be versus giving everybody the control. So we sort of set up these two counterfactual worlds, and we can look at the difference in outcomes between those two things in a trial. So the last 2 decades has seen, you know, an explosion in the use of observational data, observational cohort data, and routinely collected data in medical research. One prime example is CPRD. It's a very large database that contains routinely collected data across a network of GP practices in the UK, and it provides real-world evidence on how effective treatments are in a very broad patient population over a sustained period. So it's very useful. Let's try and make things concrete with a case study, and this leads on to sort of the first example in cardiovascular medicine. So Clopidogrel and stroke. Clopidogrel is a well-established key drug for stroke prevention in the UK. Now, you know, if we could conduct a randomized trial, and many trials probably have been conducted to assess the benefit of clopidogrel, we could very easily work out what the causal effect of clopidogrel is on reducing the risk of stroke. So I have a causal diagram here where R represents randomization, T represents whether you took clopidogrel or not, and randomization, let's assume, perfectly predicts whether you take it or not, and then the outcome Y is stroke within 12 months, and the U variable could be prognostic factors for stroke that do not influence clopidogrel treatment directly in the RCT, because randomization fixes that, but do predict your underlying risk of stroke. Now, in CPRD, we don't have randomization. We just observe that some people are given clopidogrel and some people aren't given clopidogrel. And so the decision about whether people given clopidogrel or not is going to be heavily confounded with their risk of stroke. I mean, and we want that to be the case, don't we? We want people at high risk of stroke to be given clopidogrel. But it may be that there are, other systematic differences between who gets and who doesn't get clopidogrel, based on, for example, socioeconomic factors or ethnicity, etc. So, if we wanted to use CPRD to estimate the causal effect of clopidogrel on stroke reduction, also getting an estimate on how effective it is in this in a sort of more real world context, then we need to work a bit harder, and we can use a range of so-called causal inference techniques to try and estimate this causal effect. And what we're trying to do, in essence, is to adjust for the confounding between treatment and outcome. So we're trying to measure and adjust for all confounders, or we're trying to come up with a method for getting at that effect which circumvents the need to adjust for confounders. Okay, so what's causal triangulation? I've just got a picture here of I think it was a picture that was in one of George's papers on triangulation in Nature, and then a screenshot of another paper with Deborah Lawler at the IU as the lead author, which has been quite highly cited. So causal triangulation, it's the practice of obtaining more reliable answers to research questions through integrating the results from several different approaches. Each approach has different potential sources of bias, different strengths and weaknesses, but hopefully these biases are unrelated to each other. And if estimates from these different approaches agree, then then that strengthens confidence in our findings. So that's triangulation, and causal triangulation is trying to do that with a range of causal inference approaches. So my focus has been maybe slightly different to the sort of general approach for triangulation. I think maybe it's fair to say that triangulation has generally been applied when synthesizing evidence from different data sources. So, for example, we might have observational studies and RCTs that have looked at a similar question, and we might look to see whether we can, after making suitable adjustment for confounding bias in the observational studies, that we can get, whether the observational studies tell a similar story to the RCT, or vice versa. But this talk is all about trying to design a framework for performing a sort of a quantitative causal triangulation within across a range of approaches, but all applied within a single observational study. So later on I'll call that triangulation within a study, or TWIST is the acronym I've got at the moment for it. So the first application is in cardiovascular pharmacogenetics. I worked on this with David Meltzer, Luke Pilling, Charlie Kuo, and PhD student Denise Turkman. And we had a paper published in PLOS Genetics last year describing this TWIST approach and its application in pharmacogenetic research. So just a quick summary, quick intro to pharmacogenetics. Pharmacogenetics is all about trying to move beyond giving everybody the same treatment, because that treatment may work well for some people and not so well for others, and to use genetic profiling and stratification as a way of getting everybody on the treatment that works best for them. So rather than giving everybody treatment A, we might give some people treatment A, some people treatment B, some people treatment C. Everyone experiences a better effect, and and then we experience, there's a material population health benefit. The reason I mentioned clopidogrel earlier is that it's almost a canonical example for pharmacogenetics. Clopidogrel requires CYP219 enzyme activation in order to be properly metabolized and to work to its full potential. But there's a very common loss of function variant that about 30% of the population have, but means that they can't really metabolize this drug very well. So a question we may want to ask is, how much would the population benefit if everyone could receive the full effect of treatment? And that would involve switching people who have the loss of function variant onto a treatment that worked as well as as clopidogrel does for the people without that loss of function variant. So that might mean a different drug, or it might be clopidogrel plus something else, or a higher dose of clopidogrel. So we call this the genetically moderated treatment effect. That's the sort of causal estimand we're trying to target in our analysis. So here's another sort of conceptual model for the analysis, what we're trying to estimate, another causal diagram. So we have a genetic variant G, which is whether you have the loss of function variant or not. T is the treatment, whether you get given clopidogrel or not by your GP in CPRD. Y, the outcome is stroke. But then we have an extra variable T star, which is a treatment gene interaction. Now, the loss of function carriers we can think of as, so in the non-loss of function carriers, we can think of them getting sort of two effects. They get the main effect of treatment, plus they get a boost from not having the loss of function variant. They get an extra boost. So that's represented by the sort of red arrow from T to Y, plus the extra arrow from T star to Y. Whereas in the loss of function carriers, they don't get the blue arrow, if you like. They only get the red arrow, the main effect. And we're interested in that difference. And that's what we call the genetically moderated treatment effect. So it's really, it's about the GMT is about really trying to quantify the extent of effect heterogeneity between loss of function and non-loss of function people. So what's the best way to estimate this quantity? Will more than one approach work? Those are the questions I wanted to try and answer when I first started working with David Meltzer and Luke and Charling and others. We use data from UK Biobank now and CPRD. So we really, helpfully, there's a subset of about 230,000 people who are in UK Biobank, a big cohort of 500,000 people where we have genetic data, and so 230,000 of those 500,000 people are also in CPRD. So we have their genetic data, and we also have what treatments they took. We have hospital care records, and so we can potentially do this pharmacogenetic analysis using this subset of people. And what we're hoping, in a sense, is that genetic data helps us to create a natural experiment. For me, there's not much difference between causal inference and natural experiment research. It's about trying to imagine how a natural experiment has been created. So the first estimate, which we looked at, which is really what people do as standard in pharmacogenetics, is the following. So there's an acknowledgement that the decision to take clopidogrel is heavily confounded with stroke risk. But if we make the assumption that the gene is independent of treatment, so the GP doesn't know whether you have a loss of function variant or not when they prescribe clopidogrel, and this gene only affects stroke risk through treatment, then we can think of people as being randomized into a trial depending on whether they have the loss of function variant or not. So if you have the loss of function variant, you're randomized to receive a lower level of the treatment. If you don't have the loss of function variant, you're randomized to get a higher level of the treatment. Now, if these assumptions are correct, then we can actually estimate the thing we want to, the genetically moderated treatment effect, using only treated individuals. And we can just look at the mean risk of stroke in people who are treated and who have the loss of function variant, who have a G equals 1, and subtract from that the risk of stroke in people who are treated and who don't have the loss of function variant. So a very simple analysis. When we do this in the data, so this is a table that shows the sort of summary information for people that are prescribed clopidogrel, the first column showing their age at recruitment, first prescription, percentage of female, etc., percentage of loss of function carriers. We fitted an additive hazards model to the data, adjusting for various covariates, including genetic principal components, and we worked out that being a loss of function carrier increases your risk of stroke by 0.28% per year compared to non-carriers. And this means that if we could reduce the loss of function carriers' risk to that of non-carriers, or give them the same treatment effect, then it would lead to about a 13% reduction in stroke cases. There were 110 strokes in the population of about 7,500 people who were prescribed clopidogrel, and this means that we could lower the number of strokes from about 110 to 95. That's the effect that we think we could estimate using this basic approach. But we also thought about some other approaches that we could implement. The second approach we called the robust GMT estimate. So now suppose that the gene doesn't satisfy the sort of the basic assumptions. So suppose the gene has a direct effect on stroke risk. So that's represented by this pink arrow from G to Y. Maybe it has we might call that pleiotropy. The gene affects stroke risk through some other pathway other than interacting with clopidogrel. Suppose it influences a risk factor for stroke, U here, which influences stroke, but also then indirectly influences whether you're treated or not. If either of these things are true, the basic approach, the GMT1 estimate, will give you a biased answer. However, if you essentially perform the same analysis in untreated individuals and you subtract the risk of stroke in untreated people, if you look at the difference in stroke between untreated people with the loss of function variant and the risk of untreated people without the loss of function variant, and you subtract that from the estimate that you got in the treated group, then under certain assumptions that difference, doing the analysis in the untreated people, essentially estimates the bias in the standard analysis, and when you subtract the two, you cancel that bias out. And this estimate is quite similar in spirit to something called a difference in difference estimate, which will be important for my second example. It turns out we can also employ an instrumental variable approach, or when that instrumental variable is a gene, we call that a Mendelian randomization analysis. So the MR approach is different, but again it works under slightly different assumptions. So suppose we have a gene which maybe it influences directly whether you're treated or not. We don't rule that out. There's a purple arrow going from G to T, but it doesn't affect the outcome other than through interacting with the treatment, so that there isn't a direct arrow from G to Y. So that means that the gene essentially satisfies the instrumental variable assumptions, it satisfies the exclusion restriction. If this is the case, then we can use G as an instrumental variable for the interaction between T and G. And we can calculate an MR estimate, which is the association between the outcome and the genetically predicted value of T star. So this analysis is different from the robust approach I just showed you. It also requires data on treated and untreated individuals, though. It also works in this other scenario, so in this DAG I tried to show you that there isn't a direct effect of treatment on the outcome that doesn't go through T star, and that's another way of saying that the effect is completely switched on or off by the treatment. So people who have the loss of function variant have no effect. Now, maybe that's not true. We don't actually need it to be true for the MR analysis still to be valid. So there is another scenario here where the MR analysis will still give you the right answer. So the final estimate we thought of was a method which we called the corrected as treated estimate, and it's a method that's essentially tries to adjust for all confounding by indication between treatment and the outcome. So suppose that we could measure and adjust for all confounders between treatment and outcome. For example, we may adjust for age, sex, BMI, family history, blood pressure, and we make an assumption that the treatment effect is completely modulated through T star. So what I said before, people with the loss of function variant get no effect. Then we can simply calculate the sort of adjusted as treated effect, adjusted for all the measured confounding, and then scale it by the proportion of people who are treated who have the loss of function variant, and we call that the corrected as treated estimate. Here's one scenario, one sort of diagram that tries to give you a scenario where the corrected as treated estimate will work. There are lots of other scenarios as well where it will work. I don't expect you to take this whole table in, but what it's trying to show is that we've got a range of estimates. They all have a specific formula. They all rely on a different set of assumptions. We can fit them all. We've got software to fit them all. The methods, we know what assumptions they need to work, and these assumptions are different, but in some sense they're quite complementary. Now, yeah, so we have code to fit these methods, whether the outcome's continuous, whether it's binary, if it's time to event. In each case, we try and estimate the effect on an absolute scale, on the mean difference, on a risk difference, or a hazard difference scale. And that's because we want to put all the estimates on a similar scale, but at the end of it. If we used like a logistic regression and the estimates were expressed as an odds ratio, we run into problems due to non-collapsibility, that some of the estimates may be not similar, not because they're not truly estimating the same thing, that because non-collapsibility may mean if we don't adjust for exactly the same variables, we will get a slightly different answer. Okay, so the most surprising thing of all in this analysis, when I started, I didn't really realize before, is that a lot of these estimates, most of these estimates are pairwise independent, even when you calculate them in the same data. And that means that if two estimates are independent, then they can be, if they're sufficiently similar, then it's very easy to combine them using a simple meta-analysis, an inverse variance weighted average. So, for example, we could use a simple heterogeneity statistic like a Cochrane's Q statistic. In the case of the GMT1 estimate and the corrected as treated estimate, we could calculate that statistic. If it was sufficiently small, that would give us reason to believe that those estimates were similar, and then the combined estimate, the combination of those two, the average, will be sort of guaranteed to be more precise. And for this to work well, it's my point about the estimates being on the same scale is important. So here's just a quick diagram that shows what I'm talking about. On the left-hand side, we have the GMT1 estimate and the CAT estimate for the GMTE. They're sufficiently similar because their confidence intervals overlap, and that means that we can combine them, and the combined estimate somewhere in the middle, and the confidence interval is narrower, so the estimate is more precise. On the right hand side, the estimates are very different. Our heterogeneity statistic is going to be large, and we're not going to find evidence that we can combine them. This figure is quite complicated, but all I want to show you is that we've worked out that we've got 4 distinct single estimates. There are 4 ways of combining these combining 2 estimates together. There's one way of combining 3 estimates together to get more efficient estimates, where those 9 estimates are either single estimates or made up of statistically uncorrelated estimates. So here's the results of our analysis going back to the Clopidogrel example. The first estimate I showed you was this one here, which estimated the GMT1 estimate, which estimated a 0.28% increase per year in the risk of stroke for people who are not on who have a loss of function variant. The blue the blue dots show the sort of single estimates and all the valid combined estimates. So the corrected as treated estimate is way out here. The risk difference estimate is about 10 times larger than any other estimate, and we take that as a sign that we haven't been available. We weren't able to sufficiently adjust for all confounding, so we get not a very good estimate for that. Subsequently, the black forest plot values up here are all combination estimates that involve some combination of the corrected as treated estimate and the other estimates, and those are too heterogeneous to combine, so I coloured those in black. But the most efficient estimate, we think, for this analysis is a combination of the robust genetically mediated treatment effect estimate and the MR estimate. It gives you an estimate which is quite close to the standard analysis, around a 0.3% increase per year, but the precision is improved. So that's the conclusion from this analysis. Okay, I wanted to move on to talk about a second application of this causal triangulation methods, and this is a paper. I'm describing a paper which is very soon to be submitted and has been led by PhD student Laura Gudeman, who's on the left hand side there, and is joint work with John Dennis, Andrew McGovern, Lauren Rogers and Beverly Shields and John Dennis. So yeah, it concerns type 2 diabetes therapy, and specifically second line therapy after metformin. There are many second line therapies available, for example DPP4 inhibitors, SU inhibitors, SGLT2 inhibitors, other drug classes, GLP-1RAs, etc. Here's a plot showing how the frequency of their prescription over time between 2010 and 2017. There have been few head-to-head trials of these drugs. You get DPP4 versus standard, sort of loosely defined standard of care in one trial, whereas you don't get very many head-to-head trials of DPP4 versus SGLT2, for example. Also, the population in these trials is quite narrow traditionally, so we wanted to do a much more definitive analysis comparing SGLT2 inhibitors versus DPP4 inhibitors, and look specifically at the long-term risk of a particular adverse event, a genital infection, to see which one was more likely. So we used data from CPRD from 2016 to 2019. All people in that period who were on metformin and who initiated either SGLT2 or DPP4 inhibitors, and we had data on whether they'd experienced a genital infection whilst they were on metformin, and after a certain period of either being on SGLT2 or DPP4. So one other nice thing about this data is that physician preference appears to be a strong predictor of whether a patient receives SGLT2 or DPP4. The plot on the left-hand side shows that there's quite large variation across the country at a GP level, at a CCG level, at a regional level, in whether a patient is likely to receive DPP4 or SGLT2. And this association persists even when we adjust for various factors like BMI, gender, HbA1c, age, etc., that we might think could influence whether someone gets an SGLT2 or DPP4. So we've tried to use it as an instrumental variable, as a way of creating a natural experiment again in the data, that we assume some people have had a little nudge to receive either an SGLT2 or a DPP4 just by chance of which GP practice they're signed up to in the country. Here's a diagram trying to represent the triangulation framework that we're working in for this example. We have X representing treatment, whether someone gets SGLT2 or DPP4. Y0 and Y1 represent whether someone had an infection, a genital infection, in the pre-treatment and post-treatment period. Z represents the physician preference. W1 and W0 are measured confounders, and then U represents potentially unmeasured confounders we can't see and can't therefore adjust for. We wanted in this example to estimate the population risk difference if all patients received SGLT2 versus if all patients received DPP4. So the instrumental variable approach, we assumed that we essentially used some of the data to estimate whether a GP had a slight preference for DPP4 or SGLT2, using some of the patients in each GP practice to do that, and then we assumed that GP preference variable for the remaining patients satisfied the IV assumptions. So these are essentially that the instrument Z influences what treatment people get, but it doesn't affect whether someone had a genital infection in this sort of second treatment period post either receiving DPP4 SGLT2, other than through influencing what treatment they took. So, for example, it couldn't, if some GPs were more likely or less likely to record side effects depending on the drug they gave, that would be a violation of the standard IV assumption. The corrected as treated approach in this context implemented made the assumption that there was no unmeasured confounding. So there's no U now in the causal diagram. If that's the case, then we can get an unbiased estimate of this causal effect from a corrected as treated analysis, and that's irrespective of whether Z is a valid instrument or not, or whether the difference in difference assumptions are satisfied, which I'll just come on to now. So the difference in difference approach in this context assumes that the side effect, whether someone has a side effect in the prior period, doesn't influence whether they get the assigned DPP4 or SGLT2 in the sort of second period we have data on. And we need that to be the case because that means that the sort of magnitude of the confounding bias is constant across the Y0X association and the XY1 association. So we assume that there's a constant level of confounding between whether you have a side effect in the prior period and your treatment in the post period, and then your post period treatment and your post treatment period side effect. And essentially what the difference in difference estimate in this setting does is subtract from the corrected as treated estimate the association between Y0 and X, because that is, if there's no direct arrow from Y0 to X, then what you're estimating from that analysis is the strength of confounding. So you're estimating the bias in the standard analysis, and then you can subtract it to get the true answer. We also considered a fourth estimate, which we call the extended IV approach, which actually works when all of the assumptions of these three methods, the corrected as treated, the IV, standard IV, and the difference in difference estimate, all of those assumptions are violated. But it requires there to be a non-zero interaction between whether you have a side effect in the prior period and your instrument Z. So what that means is that there must exist some GPs who, if you did have a side effect in the prior period, would allow it to influence whether you got treated or not. So that would manifest itself as a non-zero interaction in a regression model where you include an interaction between Y0 and Z, and essentially you're using that interaction as an additional instrument. So the results from our analysis, preliminary results, suggest that across quite a large range of approaches, the corrected as treated estimate, a closely related estimate, propensity score matching approach, the standard IV, a difference in difference, and extended IV approach. Well, in general, apart from the extended IV approach, they suggest a pretty similar effect that if we gave everyone SGLT2, that would lead to on average a 3% increase in the risk of genital infection compared to giving everybody a DPP4 inhibitor. The point estimate for the extended IV approach is actually qualitatively different from it's in favour of in the other direction, but the confidence interval is very wide, so it's not a very precise estimate in this example. Now, in this example, we weren't, because we're fitting a slightly different statistical model. We couldn't say anything certain about the estimates being perfectly independent. There was a higher degree of correlation, and that meant that we couldn't combine estimates in the to create a sort of combined approach and improve the efficiency. So here's a correlation plot of all the approaches, and look how correlated the corrected as treated and propensity score matching approaches are. Other methods are quite highly correlated as well, not to the extent of those two approaches. But we were able to define a generalized heterogeneity statistic that took into account this correlation, that could tell us whether any pair of estimates or any larger group of estimates were sufficiently similar to combine. So this analysis revealed that the corrected as treated and the propensity score matching estimates were, despite being very similar here and here, were actually, because they're so highly correlated, they're not actually similar enough to say that they're estimating the same thing. Whereas if we can actually combine all estimates apart from the propensity score matching approach and say that they're internally consistent, or all methods but the corrected as treated estimate, and again say that they are internally consistent because our heterogeneity statistic is sufficiently small with respect to its degrees of freedom. So that's the way that that's the sort of limit of the quantitative triangulation analysis that we could do in this particular example. Okay, just to summarize, I've tried to present a general framework for causal triangulation. The work is still very much ongoing, but the key components of the approach are to try and specify a range of methods for answering a specific question, to be clear about their assumptions, to understand the extent of their correlation, and then use heterogeneity analysis to ascertain if they're similar enough, and if so, if they can be combined to improve efficiency. All of this work has been put by me into an NIHR research professorship application, which is under review at the moment. So I'm fingers crossed that that's going to be funded. It's a long shot, but if anyone is interested in collaborating to help apply this approach in other contexts, I'd be very happy to hear your thoughts on the work. Thank you very much.
Thank you very much, Jack. That was really interesting. I skimmed the paper this morning, and I'm glad I listened to your talk, because I did need that to understand the actual paper. The way to manage this, I think, is if people have any questions for Jack, please just put them in the group chat, and then we'll do it that way. While everybody is typing, I had one question when I was looking at your one of the interesting assumptions or things I observed was that regardless of the causal model, it looked as if most of the effect estimates for your examples were fairly comparable, which is quite interesting in terms of causal inference. But they weren't always. And my question is whether you can use the differences. So you use your heterogeneity estimate to see which ones you can combine or not. And I was wondering, isn't there a lot of information in the ones you can't combine? And look at what's different about it. What's different about the causal models, and does that tell you anything about the truth, for lack of a better word?
Yeah, that's a really, really good question. I'm just going to go back to whoops. How can I go back to? Just going back very quickly to this table, if we're clear about which assumptions a method relies on, and for two methods, the overlap between those two approaches, that which assumptions are common and which assumptions are distinct, then if two methods are different, then that maybe suggests that you could think of it as being an assumption which both of those approaches relies on is not satisfied. Of course. That's if the union of the two sets of assumptions that two approaches need are all satisfied, then we know that they should give a very similar answer. But if they're different, then it becomes harder to know what to do. I think as further work, I need to drill down and really think harder about what we can infer if two methods are different. I mean, it means that they're both wrong, or that the assumptions that one method relies on, one of those assumptions is wrong, or that the assumption that the other method relies on, there must be something that's not quite right. Yeah, not everything can be true. Is I guess all the limit to things you could infer from that.
Thank you. Yeah, in a paper some of us wrote on conceptualization of natural experiment, we did recommend this methodological triangulation, and I think you show much more sophisticated than we could why this is interesting, what you can do with it. A couple of questions have shown up. They're all quite long.
I just thought just one other point on that. The reviewers of the paper also pointed out is that just because two methods are similar, it doesn't, they could be both wrong, or they could be biased. They can be biased in the same direction potentially by a single assumption being wrong, and so that's something that I need to investigate more. Systematic bias in the same direction. Okay.
The first question is from Cheryl, who asks, it's quite long. Why would you want to combine it and not just use the one that appears most plausible? I think you've answered that a little bit, but it may be good to just...
Cheryl, I think I agree. I don't want to tell people that there's one way of using this. It could be that you don't want to go down the formal quantitative triangulation approach. You may specify 4 estimators, but actually in truth, in that specific context, you think that there's one estimate which makes assumptions which are much more plausible, and you would just want to go with that specific estimate in your analysis, or you might want to give that estimate much more weight in your analysis. The quantitative framework that I've got is about combining estimates that are sufficiently similar, and if those estimates are uncorrelated, you're guaranteed to improve the precision of the estimate. So there's a gain in statistical efficiency. So just using inverse variance weighting. But if you wanted to weight using some other method which took into account how much you believe the assumptions, then that would also be potentially plausible, or to not do something quantitative at all, but use it in a more heuristic fashion.
Thank you. The next question is from Leon, who asks also about, obviously, the combining of the effect estimates, that you seem to assume that biases or assumptions are equally important, and whether there is some sort of decision tool about which estimate should be weighted as more important. For example, you may find one method producing an outlier, which should be given preferences over the combined estimate of other methods.
Yeah. Yes, I mean, both of the. I absolutely agree. when you apply these causal inference approaches, most of the time, some of the assumptions you have to make are untestable, and so you can't. Some of the assumptions, for example, some assumptions are testable for the IV approach. You can test whether it's robustly associated with the exposure, or a GP practice robustly predicts what treatment that somebody gets. We know that's true, but we don't know whether it satisfies the exclusion restriction. If you have multiple instruments, you can potentially falsify that, but you could using an over-identification test. You can never fully verify that you've identified and adjust for all confounders. So again, it's very hard to say definitively whether a corrected as treated type approach that makes a no unmeasured confounders assumption, whether that's satisfied or not. But yeah, there are lots and lots of approaches for sensitivity analyses for testing the validity of all of these different approaches, and those could very nicely be incorporated. So there's lots of scope for doing that, and those sorts of things have been mentioned in my application as further work. Absolutely.
Thank you. Eric has a question about whether you have an intuitive explanation of when different estimates can be expected to be pairwise independent despite being from the same sample.
They're kind of. I guess the intuition is that they're using separate parts of the data in a way. They're not using the full data, and so I did have a diagram sort of showing how if you create a 2x2 contingency table of the results, then you can think of some methods as sort of summing the rows of the table, and some methods as summing the columns, and those things are sort of approximately independent. So that they're using different parts of a larger data set is the easy answer. Now you may say, well, why don't you just use all of the data it's in a single model, and sort of some mega, and so I think that's something several people have said to me, is that there must be some single mega joint model you could fit that way you could estimate everything together, and that might in a sense be equivalent or possibly even slightly better than doing lots of these separate analyses and then combining them afterwards. That's my answer there.
I think the next question, Vital's question, kind of follows on from that. Where the differences in the estimate might be because the populations you are estimating the effect on might be different. And to what extent are you able to explore differences by population, and should that be included in summary tables?
Yeah. I think this question has come up a lot when I've talked to people about the cardiovascular, the first example, because people who take clopidogrel are very different from people who don't take clopidogrel. If GPs were absolutely perfect, everybody who had some non-zero risk of having a stroke would be on clopidogrel, and everybody who didn't get it would have zero risk. But actually, we know that's not true, and the method still works even if those populations are very different. They have very different. Absolute risks of having a stroke. As long as there's not complete separation between the two populations, so as long as there is some non-zero risk of stroke among the untreated, then the method still seems to work. And we are one of the reasons why I quite like triangulation within a single observational study is that this argument about populations being different, it's even more of a problem if you're doing triangulation of an RCT, one RCT in a completely different patient population to an observational study based on another population. you might get different answers because the populations are different, or the confounding structure is different across those two data sets, whereas at least we're looking at the same data set here, so there is that internal consistency.
Thank you. We have one, I think the last question from Louisa. Often we run a series of sensitivity analysis for each of the approaches. Are you extending your methods to combining results of sensitivity analysis?
Yes, that's something that we intend to do in the future. Yeah, exactly. I mean, there are sensitivity analyses for direct confounder adjustment approaches, e-values, etc. There are instrumental variable sensitivity analyses like the ones that have been developed for MR. As long as we have multiple instruments, we need, so extending the pharmacogenetic analyses to deal with a multi-valued instrument is something that's in the grant. At the moment, the work is just described for a single binary instrument. If you could extend it to a multi-leveled instrument, or even a GRS or something, then that gives you the ability to fit more sophisticated models where you can estimate bias parameters, etc. So yeah, all of that is planned as further work.
Right. Thank you very much, Jack. I don't think we have any further questions, and we're quite keen to keep it within the hour. So that leaves me to thank you for your presentation and for which was, I think, was very clear, and your explanations afterwards to our questions as well. So as you said, anybody who has specific ideas on this and wants to discuss this further, or has some ideas for projects, has to pick it up with you directly. And I think that leaves us to say thank you everybody for attending. And Jack, good luck with your application, and we hope to hear that in due course.
Well, thanks for inviting me, Frank, and thanks everybody for coming and for the really great questions.
Great, thank you. And then I'll just share the final screen. There we go, just to say that where you can find more information about this network, and to say that it's open to members of School of Public Health Research and non-members. And the only thing you need to do is just send me an email, and I'll add you to the list. So thank you, everybody, and have a good rest of the afternoon. Thank you.